Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we are happy to have here Piotr Sankowski, who is visiting from the University of Rome, where he's currently a postdoc. He finished his PhD 2 years ago.
Yes.
At the University of Warsaw, and he's going to talk about dynamic algebraic algorithms.
Thank you.
Piotr.
It's a pleasure to have a possibility to give a talk here. So we will be talking about dynamic algebraic algorithm as well as of some static application of the results. So like the outline of my talk is in the following. I'll give you some short introduction, then I will give a simple example how we can apply the algebraic approach to solve the perfect matching problem. Then I will move on to talk about dynamic algebraic algorithms. The algorithm for determinant and the inverse of the matrix, as well as for the matrix rank problem. Then I move to the application of this algorithm and talk about graph algorithm, dynamic graph algorithms for transitive closure, distances, and vertex connectivity, as well as dynamic matchings. And at the end, I will give some results about the static algorithms for finding matching in graphs as well as distances. So the techniques, methods developed here for this problem can be useful as well to solve the static problems, which is an interesting result. Okay, so what we'll be doing, we'll be trying to use matrix multiplication as much as possible. So you have this is the basic building block of what we'll be doing today. So the basic operation is you have two matrices and you want to multiply them. So the naive algorithm needs a cubic time, and in order to get efficient algorithm, we won't be using this naive algorithm, but some faster algorithms. Like, for example, if you could the idea of making this matrix multiplication faster is to divide the matrix into some blocks and do some smart calculation, like reordering of the multiplication and summing and subtracting. And if you do such thing, then you see that the matrix C can be computed with use of 7 multiplication instead of 8. And you can go, if you then use this idea which you have seen here and you'll apply it recursively, then you get an algorithm that can multiply the matrices faster than n cubed. And you can go much farther, and so we denote by omega the matrix multiplication exponent, and currently it's known that the omega is smaller than 2.376, which is a huge difference from what's n cubed was in the beginning for the matrix multiplication. So the idea between this algorithm is similar in the sense of to the Strassen algorithm. You divide in some blocks, do some really smart things, and you get this exponent. Of course, this algorithm is really not efficient, not practically efficient. You cannot take this algorithm and multiply some, I don't know, matrix of dimension 100 by 100 in this faster than the naive algorithm. So it's not practically efficient, but from the complexity point of view, it's a nice thing to know, to have this exponent. Moreover, as I said, we can multiply matrices in this time, but moreover we can as well compute some other things, like compute the determinant of the matrix, characteristic polynomial, compute the whole inverse of the matrix, solve the system of the equation, and as well, this is, which I will show you at the end of the presentation, it's it's a very recent result. You can as well in this time solve linear system of equation over polynomials. So when you have a matrix and each element of the matrix you put some polynomial, then you as well can do some manipulation and use fast matrix multiplication to get some result. And what we'll be aiming today, we'll be using these algorithms to solve some graph problems. So the basic idea is that the determinant of the matrix is sum over all permutation of the product given along the permutation. So you have a matrix, and you know that the determinant will be just a sum over all possibilities, all possible permutations. So the idea would be that we can take some graph problem and then code it into the matrix in such a way that each permutation here in the sum will correspond to the solution of the problem, any solution. And then, in order to test if this graph problem has a solution, we will just take this matrix, compute the determinant, and check if it's non-zero. Okay? And when we would like to use this idea that we encode the graph problem into the matrix in the dynamic settings, so we would like to solve some graph problem in the settings when we can add or remove edges from the graph, and so the graph changes. Then we would like to use this algebraic method, and the question is whether we can do something. Yeah? We'll see later. And the answer is yes. But what we need is first we have to we had this dynamic. The algorithm for computing determinant. So we have to devise some dynamic algorithm for computing the determinant. So this is the first step. And second step would be to show some appropriate reductions. So some reductions, computing, if you know that computing transitive closure in the graph can be solved using matrix multiplication. And this reduction goes you take the matrix and you multiply it by itself, compute the power of the matrix, and then you check if some element is non-zero in order to get the answer if there is a path from one vertex to another one. And such a reduction is not good in our case because this requires a lot of multiplication. It's not easy to see how we can get a dynamic algorithm using this reduction. Okay, so let's move to this simple example of perfect matchings. So a matching in a graph is just a subset of the edges, such that not two edges in the matching share an endpoint. And a perfect matching is a matching of size, number of vertices divided by 2. And we are interested in solving such problems like testing if the graph contains a perfect matching or finding a perfect matching in the graph, as well as finding maximum matching in the graph. So the basic idea here is that
What was the difference between perfect and maximum match?
maximum is just maximum matching, so the matching which has a maximum number of edges. And perfect matching is just matching that matches every vertex. I'm sorry, yeah, of course, I should have said it. I'm sorry?
Is it bipolar graph or general graph?
General graph. So this is general graph. The example is for bipolar graph here. So the idea of this algorithm, this reduction, is following. So we take the graph, and then we encode it in the matrix in such a way that if there is an edge from left side of the graph to the right side of the graph, from one vertex to the other, then we put some variable in this matrix. Like if there is an edge from 1 to 3, then we put here in the first row and in third column a variable. And we do it for every edge. Then, if we have this matrix, and we can compute the determinant of it. And then we get something, yes? So let's look what it is. And if we look on this determinant and try to see what it is, then we see that each variable, each monomial here, corresponds to an edge in the graph. And if we look carefully then on this result, then we see that each of them corresponds to a perfect matching in the graph. Like this one corresponds to this perfect matching, and this one to this perfect matching. And why it is so? So let's again take this equation for the determinant, and let's see what's happening. So for in each sum, the P assigns different vertex, so Pi to each vertex I. Yeah? So on the right side of the graph, left side of the graph, this is I, we have another vertex on the left side assigned. And this is a permutation, so for each vertex we assign a different vertex. So the elements of the sum correspond to perfect match. And of course, the element is non-zero if every edge here exists in the graph. So we see that the determinant of this matrix is non-zero if the graph has a perfect match. Okay. Of course, this is not an efficient algorithm because this is a polynomial, this determinant, and it can have exponentially many terms because, like, it has a lot of monomials, and so it can have like 2 to the power n or even more terms. So we cannot compute it efficiently. So the idea here is that we use some randomization. We take this matrix and substitute random numbers into the variables of this matrix, and in such way we get some random adjacency matrix. And then, with high probability, the determinant of this matrix is non-zero if this determinant was non-zero. And the idea lying behind this thing is that polynomials do not have many zeros. So if you take a polynomial and just evaluate it at random points, that with very small probability you will hit zero of this polynomial, because there are few of them. So
It's
like,
really not my idea. That goes back to Edmonds and others. So
yeah, I will give you the exact lemma in a moment. So, like, what's happening? So if we have a graph that has a perfect matching, then we can substitute something, and with some probability, even with very high probability, we will get that the determinant is not zero. Perhaps with some small probability, we'll get that it is zero. But if we take the graph that doesn't have a perfect matching, then always we will get zero here. Okay. So the lemma is due to Zippel and Schwarz, and it was like devised in 50s. So like the exact lemma is following that if we have some polynomial over some field, the polynomial has some degree, that this polynomial does not have more than this number of zeros. So let's, like, what we would like to do, so let's like take some field for some prime number of this size. And notice that the operation in this field, like multiplication, summation, can be done in constant time in the RAM model, because these numbers here has like of logarithmic length, and then the operation on such numbers can be done in constant time. And like applying this, if we take this matrix and substitute the elements from ZP into this matrix, then we get that the probability of a false zero, so the case when we have a perfect matching in the graph, and the algorithm returns that there is no perfect matching in the graph, can be bounded by 1 divided by n to the power 3. So it can be arbitrarily small. Okay, so let's move to the dynamic algorithms. So like what we would like to do, we would like to solve the following problem. We have some function which gets some results and gets some arguments and returns some results, and we would like to devise an algorithm that will support the following operation. Initialization, so that we put in all the values for the argument. We can have the update that changes one value, and the query, so we ask to return some value. And we will be solving this problem, determinant, inverse, and matrix. Like the example is here. So we are given some matrix, the determinant of this matrix is given here, and we would like to change some value. For example, changes 1 to 0, then the determinant is equal to -4. Sorry. perhaps in some cases we would like not just change one element, but perhaps change a column in this matrix. Why not? And there is when I started to work on this problem, I was not aware that there exists a solution working in this time, because it's I was really hard trying to find some results, but it was really hard because this paper is pretty old and there exists no electronic version of it. So running any search engine returns nothing. So the solution to this problem works in the following term. So we can solve this the determinant problem and the inverse, compute the inverse matrix for non-singular column updates in the following times. The update is instead of if you would have computed the determinant in every stage from scratch, then the time would be this, but we can do it in n squared. So I have to comment on this non-singular column updates. This means that the matrix, we can maintain the inverse and determinant only if the matrix remain non-singular during the execution of the algorithm. Of course, the inverse matrix is not defined in such a case, but perhaps you would like to be interested in computing the determinant, even if the matrix remains singular, becomes singular. So, yeah.
This result holds even for any rank 1 update, right?
This is for rank 1 update
Rank one.
as well. Yeah. This is I just give the simplest version. So if we have this matrix and we change one column and the determinant becomes 0, then we are not allowed to do this thing. The algorithm just fails. It cannot handle such a case. And the idea is pretty simple here. So we maintain in the algorithm the matrix A and its inverse. And what we would like to do, we would like to compute the update of the matrix is as follows. So we add some column to the matrix. So we change one column of the matrix. And we would like to compute the inverse of the matrix of this A prime. So if we do simple observations, and we see that this inverse can be written in such a way, and then every calculation here can be done in n squared time. Because if you look carefully on this matrix, then you see that you need to multiply the inverse of A by this vector V, which takes n squared time. Then you take this vector and add it to the identity matrix, and you can notice that this matrix has just linearly many non-zero terms, and its inverse can be computed in very efficiently in just linear time. So you just get another matrix which has again all then non-zero elements. So you multiply this matrix by this matrix, and this takes again n squared time. But you can do some things here faster. You can solve these problems in even subquadratic time if you allow some bigger query time. So we can support the updates faster, but then the queries cost us something. They are not for free, do not take constant time. And you can even go further, so get faster updates at the cost of longer queries. What about the matrix rank? So if you, we have seen, this basic algorithm does not allow us to do anything if the matrix becomes singular. But it can be shown that through a simple reduction that you can take any algorithm that assumes that the matrix is non-singular and turn it into the algorithm that will as well work when the matrix becomes singular. This comes only at the cost that this algorithm is randomized. This might be not randomized, but this will be. Okay, so let's move to the applications. So we would like to solve the dynamic transitive closure problem. So we are given a graph, and the queries are as follows. So is there a path from V1 to V4? In this graph, yes, there is. But perhaps you would like to delete some edge from the graph and then ask again if there is some path. And in this case, there is no path. And the history of this problem is like has already 10 years, and we can take this algorithm for the computing, dynamically computing matrix inverse, and turn them into the algorithms for solving transitive closure. And what's interesting here, that all the algorithms we get here are worst case. So each update here takes worst case n squared time. So it always works in the same time, which is pretty important in the dynamic case when we would like to apply such an algorithm somewhere. I don't know if anybody will apply it, but if you would like to apply it, then you would like to perhaps have a guarantee that each step of the algorithm will be finished in some given period of time. And then you need a worst case time algorithm.
So the others are amortized?
The other are all amortized, yes. And the idea here is, again, similar. So you take the graph and encode it into some matrix. And now the encoding goes as follows. So you take the graph, and for each edge, directed edge, like the edge going from V1 to V2, you put, again, a variable. And on the diagonal, you put ones. Okay. And like we would like then to ask a question. If there is there an edge, a path from 1 to 3, then what we do, we take the adjoint of the matrix and compute it. And the adjoint is just the determinant of the matrix when we remove from the matrix the first column and this third row. So let's do it, and we get such a matrix. So we compute its determinant, and we see that, again, each monomial is really a path, or perhaps something more complicated, from vertex 1 to vertex 3. So if you look on this, then this corresponds to this path. And this corresponds to which path? Oh, there's a wrong edge here, I think. It should be going like this. Anyway. And the other ones correspond to a path plus something, like plus a cycle. The cycle goes like this. And again, the set should be inverted, and there should be a path plus a cycle. So we see that each monomial here encodes a path, which we were interested in. And why it is so? Again, we just look on the equation for the determinant and see that, like, what's going on. So we see that every element of the sum gives a cycle cover of the graph. So for each element, we have to choose one outgoing edge. Yes, and for each vertex, we have chosen one incoming edge. So this gives a cycle cover. And what's happened? We have deleted some row and a column, and this means that, like, in this permutation, this element has to be present because it has been already taken. Like, we have taken it explicitly. So there has to be a cycle which contains an edge from j to I. And the rest of the cycle is, of course, a path from I to j. So again, we can just...
First question is this, so you know that all terms are different? I mean, there couldn't be cancellation, that you have two terms which appear, and one is a plus, one is a minus sign.
That's a good question. We know, indeed, that each term is different, because if you look, so if there are some different cycles, then the cycles differ by some edge. Yeah? And for each edge, we have taken different variable. So if the cycles are different, then the variables are different, and as well these terms are different. So there is no cancellation. Okay, so if we then we can apply the same idea. We take the matrix, substitute some random values, and then by testing if something is non-zero, we can get the answer. So we take this matrix, like we just add this ones on the diagonal, and then if we would like to test if there is a path from I to j in this matrix, then we just check if the element of the inverse is non-zero. The adjoint is related to the inverse, so for simpler notation, we can look only on the inverse. So the adjoint of the matrix is the inverse of the matrix is given. It's equal to the adjoint divided by the determinant. So in order to test if the adjoint is non-zero, you can just test if the inverse is non-zero.
In all these examples, you're actually interested in the determinant and you approximate it with the determinant? Because, I mean, you wouldn't really want the minus, but since it's algebraic, you don't care so much.
Yeah, but so, like here you cannot really talk about the permanent because you are deleting some rows and columns. So, like perhaps indeed in the a perfect matching example, you are interested in computing permanent, like checking if the permanent is non-zero. Yeah? But here you are doing something else. You take the matrix and you are really interested in a lot of like permanents, even. Yeah, because you would like to check for every pair of vertices in the graph if there is a path. And like, I don't know how to like do. That would be something like different, slightly. So, like using the same idea, you can just like take the graph and code it, and if you would like to test if there is a path, then we just look on the inverse. And this can be like because we need to like to test if there is a path. Like as I was talking in the beginning, that like the standard reduction from transitive closure to matrix multiplication requires like multiplying the same matrix several times. So we cannot use it simply in dynamic case. But here you just take the matrix and invert it. So it's really easy to use it in dynamic case. And in such a way you can just take any algorithm that maintains the matrix inverse with some update and query time. It may assume that the matrix is non-singular, and this will give you an algorithm for dynamic transitive closure that will allow to do the updates and queries in the same time. Okay, so
the results you had in your table for your results for dynamic transitive closure are randomized out.
Yes.
So these are randomized one-sided error.
Yes,
okay.
exactly. Okay, what about distances? So the problem is again very similar. So now you just would like to check what is the distance from 1 to 3, and in this graph it's 2. And if you delete this edge, then in this graph it's 0, but this edge should be inverted, and the result would be 3. And there are again some results, and like applying this technique, you can get something which is really not practically efficient or whatever, but it shows that you can solve the problem in sub-quadratic time, which is an interesting result. Because like always in dynamic algorithms, which seems to be natural lower bound is the size of the input. And the size of the input is n squared. So if you know that you can solve the problem faster, then this is an interesting result. And in order to get this result, you have to apply several techniques, like you need to apply path decomposition technique of Newton-Green, and as well some computation over polynomials. And if you do it in the right way, then you get this result. So what about vertex connectivity and matchings? So again, the problem is like we have some graph, and you would like to compute the number of paths from S to T in this graph. So in this graph it's 2. If we delete some edge, then this becomes 1. Then we add some other edge, and this becomes 2. The S and T can be common for this path. And again, like there is a way which is rather well known that you can take the graph and then code it into the matrix, and in such a way, then testing some non-zeros, zero of some determinants will tell you that there are several paths in the graph from 2 vertices. So the idea is pretty similar to the transitive closure problem. Now, as you remember, in order to test if there is a path, we have taken one element out of the matrix in order to assure that there will be a cycle which contains this element. But you can do it like with several edges. Like you can take several edges, take them out, and then you will be sure that there will be paths, cycles that contain all these edges. Yeah, so you can test for the existence of several paths in such a way. And using this algorithms for the dynamic matrix inverse, you can like test if there is compute the number of ST disjoint paths in the graph in this time, or you can just even take the graph and test if it's k-vertex connected.
So when you say they exist, do you find the paths, or do you only know they exist?
You know only that they exist. Exactly. Here you cannot
So
find.
I don't quite understand how you can take out the paths if you don't find it. So how?
You take not really the paths. The paths are left in the graph. You take just one edge. Yeah.
But then who says that you don't use other edges of the paths you had used before?
Because it's determinant, so like it's a permutation. The elements do not occur several times. So this is the idea. In each of the cycles, the elements will be different. So you'll know that the paths are disjoint. And like for the vertex connectivity, dynamic vertex connectivity, there were just few algorithms known, like one constant polylogarithmic time algorithm for undirected connectivity and two-vertex connectivity. Three-vertex and four-vertex connectivity can be done in linear time, and directed one-vertex connectivity can be solved by just transitive closure algorithm. And like in the static case, we as well would like to get some faster algorithms than what we can do in the static case. And indeed, our results, the results improves over as well over the static algorithms for testing k-vertex connectivity. Like if you compare with this, this complexity and this n to power omega becomes much smaller, and as well this terms becomes smaller. And this idea, so if you have, you know how to test vertex connectivity, then you can as well do bipartite maximum matching. You just take the graph and add some edges and checks how many paths are there. And in this way, you can find maximum matching in dynamic graph. So compute the size of the maximum matching in dynamic graph. So this reduction, of course, does not work for general graphs, but there are some other ways to do it. And you can like get the general algorithm for this. So what's interesting is that like some of these ideas we had here can be used in the static case. So like this is what the basic idea, that you take the determinant, check if it's non-zero, and you know that there is a perfect matching. So this allows us to test if the graph has a perfect matching, can be used in dynamic case, and we like would try to see if this can be used to actually find the matching. And what can be used here is the following result. So we say that an edge in a graph is allowed if it's contained in some perfect matching. So we can take this edge, like we can build a matching step by step, take the allowed edge, like build the matching, we'll know that there will exist a perfect matching that contains this edge, and we go on. Take another allowed edge and continue. And allowed edge are encoded in the inverse of the matrix of this adjacency matrix I have showed you. So we can determine allowed edge using the inverse matrix. So you can try to use this algorithm for maintaining the inverse matrix of the graph, and like dynamically, step by step, find the perfect matching in the graph. We just look on the inverse, find one allowed edge, take it into the matrix, and compute allowed edges again, take another edge, and continue like this. So we have the graph. In this graph, all edges are allowed, so we take the first one. Some edges are no longer remain allowed, so we take again one of the allowed edges. Then again, some edges may become unallowed, and we take another one, and we finish with the perfect matching in this graph. So if we would use this algorithm for finding a perfect matching, for computing the inverse matrix we have before, then in each step we need to get some information from the inverse matrix. So the fastest, like, we can use indeed one of these algorithms, the one working in time n to the power 1.575, but like we have n steps, so we need to do n updates. So the time we get is as follows. Yeah? And in this time, we can indeed, using this algorithm, find a perfect matching in this graph. But there are some like additional properties that we do not use. So we always take different edge, different vertex in this graph. So we know that if some vertex has been taken into the perfect matching, then we do not have to consider it again. That's important because then we can somehow see what has been already done and what has to be done. And we can divide these parts of the graph recursively and then use some Gaussian elimination and some lazy computation. And like the Gaussian elimination can be implemented in this time, in the matrix multiplication time. And if we use such a Gaussian elimination in this case, then we can really find the perfect matching in the graph in the same time as it's needed to multiply two matrices. So like this improves slightly over the previous result, which were like square root of n multiplied by m for bipartite graphs and as well for general graphs. So this algorithm works in the time n to the power 2.5, and we get the algorithm that works in the time n to 2.38 as the matrix multiplication. So it's improved slightly for the dense graphs. As well, these similar ideas can be used.
Bipartite result follows for flow.
The previous slide.
No, to
No, that's
Just for finding maximum flow.
It's type 1.
this one. Yeah, as well. Yeah, okay. This result can be obtained through several techniques like nested dissection, flows, a lot of ideas. I'm sorry, this result, you mean?
No, the first with the...
Here? I'm sorry, I'm lost now.
You can just...
Okay, let's go. This is wrongly written. But okay, you can find perfect matching in bipartite planar graph in even faster than this. So what you can get using this algebraic approach, you can get a simple algorithm for finding perfect matchings in planar graphs, and as well an algorithm that works in this time, like n to the power omega divided by 2, that finds the maximum matching in planar graph. And this improves over like the result for general graphs, which follows from results of Lipton-Taj, and that use nested dissection, and as well the general algorithm that apply to planar graphs gives you this time. In bipartite graphs, there are some faster approaches. I miss here one reference that shows that this can be done in almost linear time, but like you can find the perfect matching in bipartite graph only if the graph has a perfect matching. You cannot find the maximum matching in this time. So this improves over this result slightly. Okay, what about weighted matchings? So we know that we can find unweighted matchings, the maximum matching, and we can as well try to apply these techniques to find the weighted matching. So in the case of the weighted matching, we are given some graph and then weights for the edges given by some function, and we would like to find the weight of the matching is just the sum of the weight of the edges of it, and you would like to find the perfect matching with maximum weight. And here, like, we need some additional result, which is this result I mentioned in the beginning. So this result states that if you have some matrix which elements are polynomials, the polynomials of degree d, as well you have some vector, again of polynomials of degree d, so then you can solve the rational system of equations in the, like, compute the inverse of the matrix and then multiply it by some vector, and as well you can compute the determinant of this polynomial matrix in this time. So like now the matrix multiplication time multiplied by the degree of the polynomial. And you can show that the weighted problem can be reduced to the unweighted time, unweighted one in this time, like using this result of stereo. So the idea here is then that you take the matrix which encodes the graph, but you encode the weight of the edges as the polynomials. Yeah, the weight 4 is encoded as x to power 4. And then when you compute the determinant, that all edges will be multiplied, and as a result, each of these elements you will get from determinant will be multiplied by x to the power of the weight of the matching it encodes. Yes. So you can find the weight of the matching, and as well you can use this idea to really find this maximum matching. And again, I see that this is not really true, because this algorithm works only in the bipartite case. It should be written somewhere here in bipartite graphs. And the general case remains open. That's you can, for example, in general case, you can find the weight of the maximum perfect matching, but we do not find how to really find the edges belonging to this perfect matching. And again, this, if you look on the previous algorithm for the weighted matching in bipartite graphs, and these two results. So for dense graph, the time this time is n cubed, and this time is n to power 2.5 log something that depends on the weight. And here, if you take a dense graph which has very small weights of the edges, then you have a faster algorithm. Okay, what about the distances? So now the problem is as follows. We have a graph, and then we have a function that ascribes weights to the edges, and we are interested in solving the problem when we are allowed to have edges with negative weights. And of course, the length of the path is the sum of the weights of the edges, and we would like to find the distance between two vertices. So this is just the length of the shortest path. And our problem, which we would like to solve here, is just a single source shortest path problem. So we take one vertex, and we would like to compute the distances to all other vertices in this graph. And again, you can use similar encoding. Just take your graph, construct a matrix, put some polynomials that will encode the weight of the edges, and in such a way you will be able to devise a randomized algorithm for computing the distances from the given vertex in matrix multiplication time. This algorithm was simultaneously obtained as well by Juster and Zwick. So again, this result improves over the previously known results just for dense graph with very small integer weights on the edges. Okay, so to conclude, we have shown that the algebraic approach can be used to devise an efficient algorithm for the problem. So to saying we have proved that it's useful, as what I was talking about. That's a good approach. But anyway, there are few problems. The list is even much longer than this, but the interesting open problems which remain. So first one is, can we really close the complexity gap between the shortest path and transitive closure in dynamic case? You have seen that transitive closure in dynamic case can be solved in really subquadratic time, and the distances cannot be solved in this time. So, and usually there is some really strong relation between these two problems. For example, the complexities in the undirected case of the graphs are usually the same. Again, this is an interesting problem. So we know that we can find the maximum weighted matchings in bipartite graphs in matrix multiplication time. Can we do it for general graphs? Again, this is an interesting open problem. So we know that we can compute the determinant of the matrix in dynamic settings, but can we do the same with characteristic polynomial or eigenvalues? Like we have the matrix, change something, and we ask for the eigenvalues of the or the characteristic polynomial of the matrix. Okay, that's the end. Thank you.
Questions?
Yes?
Question about that, how flexible the dynamic setting that you have is. So you are allowed to replace entire columns at a time. So are you allowed simultaneously to also have updates that replace entire rows at a time? So in other words, can you mix the two?
Yeah, you can even like do some more complicated things, but like you can change even faster, like several columns or. But then it changes the complexity. But you can as well change like rows, columns, and even like do some rank 1 updates which change the whole matrix, that are like simple updates. So you can really, for example, add perhaps edges to a set of vertices, but like a simple one, a rectangular set of vertices, which whatever does it mean.
I mean, there has to be sort of some limit to how much. Obviously, if
yeah, of course.
Graph, so the boundary of how much you can change.
If you change more, then the complexity changes as well. So if you change the whole graph, then your complexity is just n to the power omega. But you can do slightly faster if you change some portion of the graph. Like it won't be n squared, but it will be faster than n to the power omega.
So you can perhaps give a whole trade-off for how much of it you're changing.
Yeah, exactly.
So I don't understand when you said you can do full rank 1. Then it's not true anymore where you have this example that there are only n elements to change. So how do you then avoid doing a full multiplication?
I'm sorry, I didn't.
Well, you had this. You had this little proof where you showed that this matrix 1 plus the rest has only n entries, and the inverse has only n entries.
Yeah, then of course
If that becomes full rank, how do you avoid that? Now you have to really do a full multiplication.
you do some multiplication, but not full multiplication. So if you have changed like k columns and k rows, then you can show that you can like gather things together and use rectangular matrix multiplication to do things faster. Then of course the time is not still, it doesn't not remain n squared, it's something bigger, but it's still faster than like computing everything from scratch.
And if you have a full rank, which changes.
Then it's an omega. That's
Oh, but before you said I didn't mean full rank. If you do rank 1, but every element.
then it's n squared. If you do rank 1 attack, that's n squared. But the proof is different. Like you have to not count the non-zero elements, but you just see that this is a multiplication of a matrix by vector, and that takes n squared.
Can you do maximum flow?
You can, but you get much less efficient algorithm that's currently known. So you can like take the graph and construct a line graph and then like test vertex connectivity. But this gives you like n to the power 6 algorithm or something. So it's not really efficient. Yes?
Any algebraic formulation for other problems like spanning tree or traveling salesman?
So for spanning tree, like you can have some formulation. You can like this is what's the name? So you can count the number of spanning trees in the graph by computing some determinant. This is a known approach, but of course this is like if you would like to find a spanning tree that you do not want to use matrix multiplication because you can find it much faster. So this is not useful. And for traveling salesman problem, so you cannot really like use anything because you could try to look on this matrix and go to some cycles indeed, but it's a set of cycles, it's not a one cycle, and like you cannot really get anything from it.
the linear systems where the entries are from some polynomial ring. What did you mean by the inverse matrix there? I didn't fully understand.
So the inverse matrix is, of course, like each element is a rational function.
So you allow in the inverse...
You are allowed to do something else. Not polynomials. In the results, there might be something more complicated, like rational functions, not only polynomials.
Is the inverse of polynomial size?
I'm sorry?
The inverse of such a thing is of polynomial size? That can be
Yes. So like it's n squared, more or less. It can be encoded in n square size.
Okay.
Like you have n in this vector, there are n elements, but you can encode each of them using a linear space. So all of this takes like n squared time.
Any more questions? If not, Piotr will be here till the evening if you want to ask.
Yes. Thank you.